We are closing the day's activity, the final day's activity. So with this, I'll introduce the today's speaker. She is Dr. Meenakshi Nerolu. She is faculty in Harvard University, I can say, College of Arts and Sciences, Harvard University. She did her PhD from Bengaluru University. She is the recipient of many awards. She won Best Paper Presentation Award in ISTAM, which was held at Pune in 2014. She has published 7 to 8 papers in international journals of international repute. She has International Journal of Applied and Computational Mathematics, then International ASME Journal of Heat Transfer. See, all these getting published, the papers in all these journals is very difficult actually. But she has done it at her young age actually. So her expertise is heat transfer. She is going to give the lecture on the same enhanced heat transfer in liquids. So between for the next 1 hour. With this, I'll hand over the session to Meenakshi. Meenakshi, up to you. Take over.
Thank you, Shikar sir. I hope you can see my screen, right? Okay. So, good morning, everyone. Can I audible? I just want to make sure.
Yeah, you are audible also.
No problem. Okay, okay. All right. Good morning, everyone. First of all, I would like to thank you, Shripad sir, and other committee members for this wonderful event and for giving me an opportunity to participate in this event. So, in today's talk, I'm going to give some brief explanation on the role of nanoliquids in enhancement of heat transfer. So when I say nanoliquid, it is combination of base liquid and nano-sized particles. So we call that as base liquid, or another name is carrier liquid. So when I say we are adding the base liquid and nano-sized particles, we are not just mixing the liquid with nanoparticles. So we have to be very careful with the particle size and the particles' behavior and their structure. So these are all the things we have to keep in mind when we combine the liquid and nanoparticles. Now, so the key idea used to nanoparticles was, so decades ago, microparticles were used to enhance the heat transfer. But the problem with the microparticle was, if you consider this pipe, so heat transfer fluid in a pipe, so what happens? So when you choose the microparticles, due to their larger size compared to nanoparticles, what happens? Some of the nanoparticles, they can settle down in the pipe's wall so that they cannot participate in the heat transfer process. So for this reason, we have considered nanoparticles so that they can easily flow through the pipe and every nanoparticles can participate in the heat transfer process. So this is the basic idea behind the nanoparticles, why we need to use the nanoparticles. So as I told, we are going to use both liquid as well as nanoparticle. There are some common choice of base liquid or carrier liquid. So in my problem, I have considered 4 liquids. So it is categorized as inorganic and organic. So water is inorganic solvent, and other organic solvents are like ethylene glycol, engine oil, and glycerin. There are some other base liquids that are like methanol, alcohol, silicone oil, kerosene, and so on. So I'm mainly concentrating on water and these three organic solvent. Along with that, we considered 5 nanoparticles like copper, silver, they are like metals, and copper oxide, aluminum oxide, and titanium. So these are all metal oxide. And again, these are not only the nanoparticles, there are other nanoparticles, like there can be nanotubes that can be used as nanoparticle to add to the liquid. So other nanoparticles like gold, graphene, silica, iron, and also, as I told, you can also use carbon nanotubes to combine with the liquid. Now, so with that in mind, so we have considered total 5 different types of nanoparticles. So nanotube, I'm not going to explain this one. We considered only 5 nanoparticles, and we combined this with the different types of liquid. So total 20 combination of nanoliquids are considered for this problem. So what happens? So whenever you choose nanoparticles, so you have to be, we have to be very careful with the size. So the size of the nanoparticle, usually it will be between 1 to 100 nanometer. So this is the microscopic view of the nanoparticles that we have considered. So the size of the nanoparticles matters. So we have to be very, very careful with the size of the nanoparticles whenever we choose our model. Now, as I told in the beginning, so when we compare the nanoparticle with the microparticle, we saw that they have high surface area. Nanoparticles has high surface area so that they can increase the heat capacity of the liquid. So that is the main advantage of using nanoparticles. Now, whenever you change the size or shape or material or volume fraction of the nanoparticles, what happens? Absorption of thermal energy can be maximized. So these are all the important features of nanoparticles that we have to consider. Now, along with that, the main idea behind the nanoliquid is thermal conductivity. So we know that the thermal conductivity of nanoparticle is high compared to the liquid. So that is the key concept behind the enhancement of heat transfer. So these are all the main advantages of using nanoparticles. And if you combine with that liquid, we'll get nanoliquid. So these are all the main idea of using nanoliquids. Now, along with that, so whenever we use nanoliquid, so it can be used as coolant in heat transfer equipment, such as heat exchangers or electronic cooling system and radiators and so many other applications in real life. Now, with that in mind, so with the application of nanoliquid and other usage of nanoliquid, we have to make some assumption in order to do the mathematical modeling. So here we are going to consider small scale convective motion, because as theoretician, we have to make some assumption, because we are not doing, in this case, we are not doing the experiment. So the engineers and other simulationists, they will do the experiment with this, some of the assumptions that we do, theoretician do. So whenever I say assumption, the assumption that we are going to consider in this particular problem is the shape of the nanoparticle. So there are different kind of shape of the nanoparticle. So as I told, whenever you consider a carbon nanotube, for example, that can be cylindrical. So there are many other shape. So that depends on the shape factor of the nanoparticle. But in this current problem that I'm going to explain, so the assumption was the particle shape was spherical. So we are going to consider the shape of the particle as spherical, and the size of the nanoparticle will be between 1 to 100 nanometer. And there will be uniform distribution of nanoparticles in the liquids. This is another assumption. And we are going to consider only dilute concentration of nanoparticles. I'll tell you why we have to use only dilute concentration of nanoparticles whenever I explain the mathematical modeling part. And there will be thermal equilibrium between carrier liquid and nanoparticles. This is another assumption that we are going to make. And nanoliquids considered are Newtonian Boussinesq liquid. So whenever I say Boussinesq, you are familiar with that. So the density is constant throughout. Now, and also we are considering small scale convective motion and laminar convection. With this assumption, so I'm going to explain different kind of models that we have to consider whenever we study Rayleigh-Bénard problem using nanoliquid. So there are two models available to study nanoliquid. One is single phase model. Whenever I say single phase model, it is local thermal equilibrium model. There is a thermal equilibrium between liquid and nanoparticles. The other model is Buongiorno two-phase model, and that is local thermal non-equilibrium model, and generalized Buongiorno two-phase model. So in these cases, what happens, as I told, whenever you have single-phase model, there is a thermal equilibrium between nanoparticle and the base liquid. But in the case of two-phase model, there is thermal non-equilibrium between carrier liquid and nanoparticles. Due to this, what happens, there will be 7-slip mechanism, of which Brownian motion and thermophoretic effect are dominant. I hope these two-phase models that are already discussed by Dr. Kanchana and Dr. Lakshmi in the previous lectures. So in this talk, I'm mainly concentrating on single phase model. That means there is a local thermal equilibrium between the particle and liquid. Along with that, so this is not a usual Rayleigh-Bénard setup. So we are going to use an external mechanism to the entire Rayleigh-Bénard system. So there are different kind of regulatory mechanism. So it is classified as two types of regulatory mechanism. One is internal and another one is external. So whenever I say internal, it can be non-uniform basic temperature gradient, or it can be heat source modulation or heat sink modulation. So these are all the internal effect to the entire Rayleigh-Bénard system. And the external regulatory mechanisms, it can be rotation, or it can be magnetic field, or gravity, temperature, and rotation modulation. So these are all different kinds of regulatory mechanism for Rayleigh-Bénard convection. So I'm concentrating on gravity modulation. Again, so there are a lot of assumptions here. I mean, a lot of models that we are going to use here. So whenever I say gravity modulation, again, I'm going to consider three types of gravity modulation: sine wave, triangular wave, and square wave. So more about these waves, I'll explain whenever I explain the mathematical modeling. So there are three kinds of gravity modulation I'm going to explain: trigonometric sine wave, symmetric triangular wave, and square wave. So with all these assumptions and the models, we are going to formulate mathematical equation. So it has to be very, very important to consider all the models and assumptions whenever we in the sense theoretician formulate the mathematical equation for the given problem. Now, as I told, we are going to use Rayleigh-Bénard setups in such a way that there are two horizontal plates in such a way that we are heating the bottom plate, and these vertical plates will be at a distance h apart, and nanoparticles are uniformly distributed in the system. And as I told, I'm going to consider a vertical vibration. Whenever I say gravity modulation, So the system is vibrated vertically. So there is a vertical vibration in the entire system. Due to this, what happens? The gravity will be depending on time. So the gravity will be time dependent because of the vertical modulation. And we call that as G jitter or gravity modulation or time dependent body acceleration. So there are synonyms. You can call it by any names. So this is the basic idea behind the gravity modulation. So you are going to put up the system vertically. So there is a vertical modulation in the system. Now, the governing equations of the entire problem is conservation of mass. So, you know, this is Q represents velocity and conservation of linear momentum. Now, here you have to make an observation. G is depending on time. So this is the key idea behind the entire problem. We are considering gravity modulation and the conservation of energy. So these are the governing equations concerning the current problem. Now, so whenever I take the governing equation, so all the physical properties that have chosen is nanoliquid properties. So whatever the property of physical properties we have taken, that is of nanoliquid, not a regular liquid. So whenever I have to find dynamic viscosity of nanoliquid, so we have to use Brinkman model. There is other models like Einstein model and other models. So whenever I choose dynamic viscosity of nanoliquid, I used Brinkman model to calculate dynamic viscosity of nanoliquid using this formula. Similarly, to conduct uh, to calculate thermal conductivity of nanoliquid, we have Hamilton-Crosser model. There are some other models like Crozier model, Maxwell-Garnett model, and other models. Now, this is the general Hamilton-Crosser model to find out the thermal conductivity of nanoliquid. Here, since I have assumed the particle shape as spherical, so this value, the value of n will be the shape factor. So since we consider spherical shape, this value will be equal to 3. And for n equal to 3, if we calculate the thermal conductivity of nanoliquid, we require thermal conductivity of nanoliquid. So this is using Hamilton-Crosser model. Now, and other properties of nanoliquid are chosen from mixture theory. So these are the basic idea behind the problem. So with that, we use a regular procedure. We have to use the quiescent state to get the solution in the form for the temperature and density. And other common procedure we follow, that is, we have to consider the perturbation on quiescent basic state. So where prime denotes the perturbation. Now, since we consider only two-dimensional disturbances, I used to introduce stream function. It is given by u prime equal to this equation. So with that in mind, so we have to eliminate pressure from the conservation of momentum, and using non-dimensionalization, what we get is vorticity equation and heat transport equation. Now again, the main concentrate is on gm tau. So it is gravity which is depending on time. Now, once we get the vorticity and heat transport equation, so these are the nanoliquid parameters. Once we use the non-dimensionalization, we get all these parameters. Once we get the vorticity and heat transport equation, we have to solve those equations by using boundary or periodicity conditions. Now, in order to solve the vorticity and heat transport equation, we use perturbation method, and the asymptotic expansion considered for Rayleigh number and psi and theta is given by this one. So that is perturbation technique. Here RA naught is nothing but critical Rayleigh number. Now, so we have to be careful with the asymptotic expansion. Here, this is valid only for epsilon less than 1. So that means it is obvious that we are considering small scale convective motion. So this is valid for epsilon greater than, less than 1. So epsilon square is nothing but amplitude of convection. So once we have asymptotic expansion, so I'll write vorticity and heat transport equation in the matrix differential operator form. So it will be easier to simplify the solution. So once we have the matrix differential operator, again, so here we can see that we are using the small scale convective motion. So, and I introduce the small scale convection here, that is for time epsilon square tau. And also, so in the equation we had gm of tau. So that is nothing but, that is for gravity modulation. So as I told, there are three types of gravity modulation: sine wave, trigonometric sine wave, triangular wave, and square wave. Now, so for different waves, you have to consider different gm of tau. So it varies for different types of waves. Now for sine wave, we have gm of tau is defined as epsilon square delta 2 sine omega tau 1. So it will be in the form of sine wave. Now whenever I say triangular wave, that is nothing but Fourier expansion of infinite series of sinusoidal wave. So whenever, so here you have to be very careful. The number of harmonics will be always odd, and whenever you take n as large enough, what happens, this sinusoidal wave will be converted to triangular wave. So for as n approaches infinity, so this function will be reduced to triangular wave. Similarly, for square wave, you are considering odd harmonics, and whenever n gets larger and larger, sine wave will be converted to square wave. So these are the basic waves we are going to discuss now. So this is the schematic representation of the same. So sine wave, triangular wave, and square wave. So by considering all this information, so we are going to solve the vorticity equation, and we are substituting for the asymptotic expansion and simplifying the vorticity and heat transport equation. You will get different system, different order of system, that is first order, second order, and third order system. So once you have these different order system, so you have to find out the solution for this one. So in order to find the solution, I'm going to consider boundary condition again. Using these boundary conditions, we get the solution for first order and second order system. Now, so using the first order and second order system, we can find out the critical Rayleigh number where the onset of convection sets in. But I'm not interested in third order system, but still we need to find out the amplitude. To find out the amplitude of the given problem, so you have to consider the solubility condition. So whenever I say solubility condition, in order to formulate solubility condition, we require that the solution of the adjoint of the first order system. So we know that the first order system is LV1 equal to 0. So the solution of this first order adjoint of this first order system, it should be orthogonal to inhomogeneous term in the third order system. In the third order system, we had R31, R32 transpose. So it should be orthogonal to the inhomogeneous part of the third order system. With that in mind, we get the solubility condition. It is given by this equation in order to find the amplitude of the given problem. So once you use the solubility condition, we get the corresponding first order differential equation that is well known as Ginzburg-Landau equation, or we call this as Bernoulli equation. So whatever the procedure I told till now, it is for sine wave. The same procedure you follow for trigonometric and square wave, and you will get the corresponding Bernoulli equation for triangular wave as well as square wave. So once we have the amplitude equation or Bernoulli equation, so this is not analytically tractable because of the time dependent. So to solve this, we have considered numerical solution, and we used Mathematica ND solve to solve the Bernoulli equation. Now, the main idea behind the problem is to verify the enhancement of heat transfer. To do that, we have to introduce Nusselt number that will tell you the amount of heat transfer in the given problem. So this is the expression to find out the Nusselt number, which will quantify the amount of heat transfer. Now, so this is the simplification of integration, and you'll get the Nusselt number. Now, as I told, we are considered the gravity modulation. So whenever you have the modulation, you have to take mean Nusselt number, time averaged Nusselt number. That is nothing but mean Nusselt number given by this equation. With the value of this mean Nusselt number, you can tell whether there is enhancement of heat transfer or not. So this is the basic idea. So I'll come to the results and discussion. Now, with that mean Nusselt number, you have to calculate the mean Nusselt number for different nanoliquids. As I told, we have considered 20 nanoliquids, and we calculated mean Nusselt number for different waves, that is triangular wave, trigonometric wave, and square wave, and compared the result with without modulation. What happens to the Nusselt number with modulation and without modulation? As a result, so what we have observed was mean Nusselt number of, so this, whenever I say WM, that is without modulation. So if you consider with modulation, out of 3 gravity modulation that we have considered, square wave has the highest Nusselt number. That means it transfers highest heat compared to trigonometric triangular wave and trigonometric sine wave. Now, if you see the behavior of these 3 modulations, we can also note that the area which has highest area under the curve, that will transfer maximum heat. So in this case, the square wave has highest area under the curve. So it will transfer maximum heat. The same result we get when we find the Nusselt number. So this is what we have got from our result. Now, when we compare the different types of, the different mean Nusselt number for different values of delta 2. So here, delta 2 in the sense amplitude of modulation. Here we observed that when you increase the amplitude of modulation, the mean Nusselt number will increase. And again, for square wave, it will be the highest compared to sine wave and triangular wave. Similarly, if we consider the frequency of the modulation, whenever you increase the frequency of the modulation, the Nusselt number decreases. That means that there is a diminish in the heat transfer. So, and the last one is the volume fraction. Whenever you increase the volume fraction, we can see that there is increment in the mean Nusselt number. That means addition of nanoparticle increases the heat transfer. That means there is an enhancement of heat transfer by the addition of nanoparticle. So these are the highlights of the study. So to come to the conclusion, as I told, whenever we consider 3 different types of modulation, the area which has the highest area, the wave which has highest area under the curve, that will transfer maximum heat compared to other areas. Same thing we will observed in mean Nusselt number. And nanoparticles advance the onset of convection and it enhance the heat transfer in carrier liquids. So the presence of dilute concentration of nanoparticles in the carrier liquid is to enhance the heat transfer. So this is the basic idea behind the problem. Now, so with all these models and ideas, so the next research plan is to consider hybrid nanoliquids. Whenever I say hybrid nanoliquids, so instead of one nanoparticle, we are going to consider two nanoparticles and what happens to the enhancement of heat transfer. So these are the basic ideas of nanoliquids. So with different models and methodologies, so it will be used to identify which material is suitable for heat transfer enhancement or cooling. And also it is important to note down the cost of the material. So depending on the cost and enhancement of heat transfer, you can decide which material you have to choose. So these are the topics related to my talk and some of the references. And thank you for this opportunity.
Hello.
Yes. Yeah.
Thank you for your very nice lecture. You have proved. I have listened to your presentation earlier also at ISTAM, where you got best paper presenter award. So it was a very nice lecture. I request the participants, if they have got any questions, they can raise their hand and they can ask the questions. Any questions?
I'm happy if there is no question.
I believe that they have followed everything 100%.
Hopefully.
Yeah. So if you have got any doubts, you can pass it on to me. I'll pass it on to her and I'll get the answer for that. Or I'll share her email ID. There is no issues. So with this, we are closing to a first session of the day. For us, it is for all the participants, it is a daytime, but for her, it is. I should tell her good night. Huh? Okay, Meenakshi. Thank you for
so
your
much.
nice lecture. Thank you for accepting my invitation. Thank you.
Thank you so much.
Okay. You can leave. You can leave the session. No problem.
I will attend Pranish sir's and I will.